Já começou, já? Eu posso dar um ok para o chat? Tem que postar. Pode fazer enquanto está. Faz aí. Acho que tá tudo certo. Nossa, dá super pra ouvir, vou ter que bater na bola. Desligado. Quê?
Okay, good morning, everybody.
Good morning.
Okay, so for today, let's try doing it a little bit differently than yesterday. So yesterday, I tried to go through all the problems in one session without a break. So I think it will be better if we make the break a bit sooner today. So maybe I'll start with something unrelated to yesterday's contest. I will talk a while about some of the social aspects of competitions. Then I'll go through a bunch of the tasks from yesterday, we'll have a break, and then we'll see how much time we have left. We'll go for the rest and maybe also address some other topics. So, in order to start today, I wanted to talk about things like contest strategy and approaching problems and training. It's not an easy thing to prepare oneself for competitions like this one. You are competing against the best people around the world who are also doing their best to prepare, and there's only a limited amount of time we can spend on these activities. So it pays off if you can practice and if you can prepare yourself efficiently. So when you are thinking about doing practice for programming competitions, I think that the first question on your mind should be the question of expected value. What is the action, or what should I do to maximize the expected benefits I will get from these actions? And the answer isn't general. The answer isn't the same for everybody, because each of us is somewhere else on the spectrum of being the top competitive programmer worldwide. So for each of us, different actions may bring different rewards. At the beginning, when you are only starting with these competitions, usually the first bottleneck are your implementation skills. So when you can come up with an idea for a solution to the easy task, but then you spend an hour and a half hunting bugs in your code, and then you realize that all the time it was a simple integer overflow because you were careless and you didn't think about the limits enough. So if this happens to you, the main thing you can do is practice this implementation-based stuff. Stay with the easy problems, take solving the problem kind of out of the equation. Just have a bunch of problems where you already know what to do, and you just have to do it and go through them. Find out the hard way all the bugs you can make, such as not paying attention to the limits or making an array one cell too small and then having array overflows, or I don't know, in binary search, getting the plus and minus ones mixed up. And these are things everybody will do when they start with programming. And the sooner you get them out of your system, the sooner you find out patterns, how to write code to prevent this from happening, then the better for you. And this will also give you the most improvement, because you will stop wasting a lot of time at the competitions, and at least you will be able to get the easy problems, score those points, and then still have some time left for the rest of the competition. So this is, I think, the first major step you need to have. You need to be able to trust your implementation skills reasonably well. And also, one thing that helps is mechanizing some of the patterns that come up frequently. For instance, if you implement breadth first search for the first time or seventh time, you still probably have to think about it. You still have to spend time thinking, okay, now I have to declare a queue, and the queue has to be of the right type of the items I'm pushing into the queue, and then I have to do, and so on and so on. If you are writing a breadth first search for the 100th time, it's already completely mechanical. You already know what you are doing, you already have your established pattern, I'm doing this, then I'm doing that, then there's a while cycle on it. This already comes without thinking. You know it's correct, and you are freeing up your mental capacity to think about the actual important parts of the problem. How exactly do I use the breadth first search? What is the graph I'm using it on? Are there zero length edges or not? If they are, how do I modify the breadth first search? This allows you both to be faster and to avoid stupid mistakes. A very common example is when the graph involves, for example, a chess piece. If you have a chess knight, the knight has 8 possibilities how to jump. And a common beginner mistake is when you're writing code that is searching through all possibilities how a knight can reach different cells on the chessboard. You will write a piece of code where the knight tries to jump -2 rows and -1 column, and then you copy it and paste it 7 more times, and then you forget to change the pluses and minuses and ones and twos in some of those places, and welcome 5 hours of debugging and never getting it right. So once you learn a pattern, how to write searches, once you learn that it is a good idea to start by writing 2 arrays of constants, the x of movement, the y of movement, and then when trying all possibilities how to move the chess knight, it's just a for cycle that iterates over those 8 possibilities. You don't write duplicate parts of code, you write each part of code just once. If you want to use it 8 times, you wrap it in a cycle. And when you learn tricks like this, it will make your implementation faster, it will make it less error prone, and it will allow you to focus on the more interesting parts of the problem. So this is something you need to get working first. And one good thing you can do is after a contest, if you have the possibility to do so, take a look at the implementation of the top contestants. So look at what you did in the contest, then take a look at the top 5 people who won the contest. And if you can do so, for example, on code courses or top coder, you can do it. You can take a look at how they implemented the same task. And quite often you will find that your implementation had 100 lines of code, their implementation had 7. They knew a trick, or they thought about a better way of implementing it. And quite often you can learn how to do stuff in a smart way. For instance, there are many different things, many tricks you can use to not just improve the efficiency of your code, but decrease the amount of bugs you will make. One of the favorite examples of mine is using references in C++ when doing memorization. So you have a recursive function, a function that, for example, returns an int, is called solve, and has some arguments. And then the usual pattern for memorization would be that you take a look at your memorization table, you check whether these arguments have already been solved before, and if yes, then you return the value, and if not, then you compute the value, then you store it into the table, and then you return it. And here's a possible place where you can make a bug. You can forget to memorize, you can forget to store the computed value into the table. And one easy trick how to avoid this is not to compute it separately, but to compute it directly in the table. And one way to do this is, so we have some kind of a map or something, which is called memo. And first we make a check whether args is present in the memorization table. So in C++, this would be something if memo count args is greater than 0. And if you are lazy, you can omit the greater than 0 because the count will either return 0 or 1. So you just know it with the Boolean value. Then you return it. And in the opposite case, what you can do now is you can declare a reference to the actual cell in the memo table. So we will make something like this. Int at result equals memo of those arguments. And right now you can just use, so this is like giving the new symbolic name to this particular cell in the memo table. So you can now use the result just as you would use an ordinary variable. You can compute the actual result you want to return in these variables. And at the same time, it is getting memoized already. So at the end, you just return it, and there is no way for you to forget to memorize. And this is, like in terms of problem solving, this doesn't matter at all. This doesn't change the algorithm at all. But in terms of implementation, this is a tiny edge. This is a small fraction of a percent you just gain. Because when you compare, now when you compare yourself to another person who doesn't know and use this trick, maybe in one of 100 problems, it will happen to them and they will forget to memorize and they will make a submission that you'll have a time limit exceeded. And suddenly you gained 25 minutes in this particular contest. So it's a tiny edge, but it is still an edge. And if you want to be good, you don't need strategies. But if you want to be the best, then each and every such tiny edge can help. So, yeah, expected value of things you do. It's if you are somewhere at the beginning, things like this doesn't matter. You focus on correctness, focus on writing nice code, focus on thinking in invariants, focus on taking writing code one step at a time. This is also one very important trick that can help you write code. A common mistake is that you try to write the solution all at once. So you sit down with the keyboard, you implement the solution, then you try running the example from the problem statement, and it doesn't work. So you start debugging. A much better pattern, especially if you are making bugs in your implementation, is to approach it more modularly, to think about writing the solution one conceptual step at a time. So if the input is difficult to parse, definitely just start by writing the input parsing routine and then test it. So at this stage, even though it doesn't solve anything yet, take the example input, maybe create one or two inputs of your own, and test whether this part of your solution works. Only if you are happy that everything works and you all exactly know what is where stored in your variables, then you continue on with the next step of your solution. And after each step, if you spend a few seconds checking whether everything works as expected, it will be much easier for you. For instance, because you will not have to hunt the first bug in your entire source code, you can start by assuming that the bug was introduced in the last conceptual part you implemented. So this is a very good lesson. If you are getting stuck in a debugging loop and if you have problems writing code that works on the first run, then do it like this. Do it modularly. Try to take each logical step and maybe you wrap it into a function so that you have the code divided into nice smaller pieces. And this really helps. Another thing that helps, especially if you have problems with implementation, slow down. Because by slowing down, you will be faster. It sounds like a paradox, but it isn't. Because the reason why you are making so many bugs when you are implementing stuff is because you are trying to go too quickly. You are trying to go faster than you are able to. And this then leads you to being careless, this then leads you to forgetting corner cases, this leads you to skipping through some important conditions and so on. And if you slow down, if you take a more methodical approach, if you try to think about each step we were making and making sure we're not forgetting everything, in the end, you will have the problem solved faster. And yeah, this also has been happening to me when I was taking part in contests, and like what you are then trying to do is obviously you are trying to go as fast as you can, and from time to time you will start going too quickly, and you will start making those mistakes, and periodically you have to come back and tell yourself, okay, now I need to slow down for the next few contests. I need to take a slower, more methodical approach because I'm already trying to be too fast, and already the benefits of being faster are outweighed by the disadvantages from making more mistakes. So there's a trade-off. You have to find the balance for yourself. All right, and when we finally get the implementation to a state when we are happy with it, now comes the really interesting part, which is problem solving. This is the thing that's the most fun. This is the thing why we are doing it. We want to solve problems. We want to learn how to solve hard problems. We want to be better at solving problems than the other guys here. And so how do we do it? What is a good way to maximize the expected value we get in training? To show you my way of thinking about this, I will start by giving a slightly different example. So imagine that you have a class and you want to test how good they are at, for example, solving programming problems or solving mathematical problems. What you can do is you can give them an exam, you can give them a contest, you can give them some problems to solve. And now what happens is that if you give them problems that are too easy, the results of the exam will not tell you anything useful about their problem solving skills. Like everybody will solve everything, modulo some random noise. So what you will see in the results of the contest will be the random noise. Who got luckier, who made a smaller mistakes, or maybe if you don't have any feedback, you just write your solutions and maybe make a small mistake out of the north side, then suddenly you lose points for something that you could solve. So you will look at the results of the exam, and you will not know anything about their problem solving skills. You will just see the random noise. If you give them an exam that is way too hard, you will also not learn anything about their problem solving skills, because you will see results where there is roughly all zeros and maybe a point here and there. Again, somebody maybe got lucky and knew some of those concepts, some of those hard tasks, but you didn't gain much information. There is a lot of theory about measuring information about in this way. It's called Fisher information, and essentially you can measure the amount of information you get if you give a person with a skill level like this, or a task that is hard like that. And there are ways to actually model things like who is a better programmer and which task is how difficult. I will not go into the details now, but it's a very interesting area with a lot of potential. There's still a lot of things we don't know, but it's there's also a lot of things we do. And essentially, in order to find out how good a person is, you need to give them an exam of roughly the appropriate difficulty. A very similar thing is happening, for example, at the IOI or the ICPC or any of these other programming competitions, when we are trying to set problems for such contests. If you just want to determine, for instance, the absolute winner of the ICPC or the absolute winner of the IOI, what you should do as a problem setter, you should give them a bunch of hard problems. Because the hard problems will be those that will make the most difference between the people at the very top. But if you give an IOI or you give an ICPC finals with 6 or 12 or hard problems and nothing else, then precisely what will happen is that we will get a lot of information about the people at the top. So for instance, the top 10 will really correspond to their skill levels and will be very consistent. If you will do it 10 times, you will see roughly the same top 10 each time. But then at the bottom, there will be complete random noise because the tasks used didn't give you any useful information about the weaker teams, about the weaker contestants. And this is not what we are trying to do. At the ICPC, we want to have everybody to have fun, so there should be something easy. We want the ICPC World Finals, for example, want to have regional champions in different regions at different skill levels. At the IOI is giving out a bunch of different medals, so there's like gold medal, silver medal, bronze medal boundary. Approximately half of the contestants should get the bronze medal. And again, in order to award these medals to people who actually deserve them, it would be better to gain a lot of information about those medal boundaries, to be reasonably certain about those medal boundaries. So what this boils down to is that the problem set should somehow cover a broad spectrum of difficulties of problems because we have contestants with different skill levels. And this is how good problem setting is done for these competitions. But the problem setters spend a lot of time tweaking the difficulty levels of different problems, of different sub-problems, just to make sure that a lot of spectrum of skills is covered by this task as well as possible. And why am I mentioning all of this? Well, first of all, because we always need new problem setters as well. So at some future parts of your career, if you are interested in teaching, in this way giving back and helping the next generation of people grow and be better problem solvers and build a better world and so on, then by all means we'll be happy if you join our ranks and help us set even better contests. But the other thing, the other reason why I'm mentioning this is that this is very closely related to practicing, to learning problem solving. Essentially, if you practice on problems that are too easy for you, you will not learn much new in terms of problem solving. This is good practice for implementation, this is good practice for consistency, this is maybe good practice for speed, but it is not good practice for problem solving. If somebody gave you those problems as an exam, they would already expect you to solve all of them because they know they are too easy for you. So by solving such problems, you are making yourself feel good. Yeah, I'm solving all the problems, I'm already advancing the world rank list as spoiled or somewhere. I have 170 problems solved. Wow. But you are not advancing your problem solving skills. On the other hand, if you are trying to solve problems that are too hard for you, you are also not advancing your problem solving skills. You will spend some time looking at the problem, you will spend some time analyzing the problem. This may help you a little bit, it's not time completely wasted, but in the end, you will be forced to give up on most of those problems, and you will have to go to the editorial or solution write-up or ask somebody else, how is it solved? And you will learn a little bit, but you will learn slowly, and you will not learn deeply enough. So it will take multiple occurrences of seeing the same problem and before you will be able to solve it actually on your own. It will work, you will do something, but it will be too slow. So the sweet spot, the right place when you are learning enough, when you're maximizing the amount of you learn in terms of problem solving, is solving problems that are just on the top end of the spectrum of what you are able to solve. So the problems should be hard, but they shouldn't be so hard that they are unsolvable. A good measure of doing it right is that when you are practicing problem solving, when you are attempting to solve these hard problems, you should get a significant fraction solved, and you should fail to solve a significant fraction of those problems. So for example, if out of every 10 problems you attempt, you solve 6, you are doing it right. This is the sweet spot. This is where you are learning the most. And this is also why it is so hard to be among the top contestants in the world, because not everybody is mentally equipped to deal with such a situation, and not everybody does actually realize this. And this is like maybe considered a closely kept secret of the contestants, so now pay attention. For many people, what happens is that solving problems is fun, and failing to solve problems is not fun. Failing to solve problems is boring, it's depressing, and if I fail to solve a problem, it tells me that I'm a failure, and I have no place of attempting to even be good at these programming competitions. I should find something else to do. And for many people, this is actually what will happen. They have fun solving the easy problems, then they will try to solve some of the harder problems, on some of them they will fail, and for them this will be an indicator that they are not good enough. They will give up, or no, maybe not. It may not be a conscious choice to give up. It will just be that, yeah, I'm solving this. Now there are these hard problems, and I'm not good enough. I'm not having fun solving them, so I will give up. I will play games instead or something. And this really happens, and in this way you will lose a lot of your concurrents. But if you think about it, if you realize what you are doing, if you are aware that I'm doing the right thing, if I'm failing to solve some of the problems but still succeeding in others, this means I'm doing my best to improve myself. And if you can convince yourself that this is the right thing, and if you are confident enough to be also able to accept your failures as part of the training process, then this can give you a very significant edge. And I have to admit that I was lucky in this because to me this kind of came naturally. To me this I never had issues with my confidence, and I just accepted yes. Well, problem solving was still fun, even if I failed to solve some problems. If anything, failing to solve problems was a challenge. That okay, in the future I'll come back and I'll get this problem right. Something like this, but yeah, like each and every one of us is different, and for some of us, this may be a significant bottleneck. So I hope that now that you heard some of this said explicitly, that failing isn't wrong, failing is good for you. Failing is a reasonable portion of the things you attempt means that you are doing the best thing you can. If you can convince yourself that this is true, and if you can use this to your advantage, then I think this may be the thing that will help you the most. So this same thing then should apply also to the practice contest we have here. It's not a shame not to solve everything, but it is a shame to give up, and it is also a bad idea to just let these things go away. One of the most important parts of practice for most good competitive programmers is it doesn't have any actual English word, but the word used in the community comes from Russians who came up with the new English word absolving. So absolving means that after the contest you still come back and you try actually implementing and submitting solutions to the problems you failed to solve in the contest. Why does this matter? Because the spectrum is not black and white. It's not you first learn how to do the implementation and then you learn how to do problem solving. It's kind of a bootstrapping process. You have to switch back and forth between those two. And in particular, many people get stuck at a place where they can already implement easy solutions. So if the solution is under 30 lines of code, if the solution has one conceptual step, they can get it right. But if they encounter more complicated problems where you have to do multiple steps in sequence, or maybe write some more complex code, some harder data structures and so on, they will get stuck. And this is why you need to switch back and forth. You need to spend, even if you are a top contestant already in terms of problem solving, you need to spend some time on implementing these hard problems. And again, there are new tricks to be learned when implementing, for instance, hard data structures. There, maybe 10 years ago, it was unthinkable to set a problem that would require the contestants to implement their own balanced binary tree. Balanced binary trees were considered to be something crazily complicated. And maybe you would have one in your ICPC notebook with you, but it would be 3 pages of code and nobody would really be willing to retype it during the contest. But nowadays, we know implementations of trees that are 10 lines of code, for instance, the GUI and everything you want to do with them. And suddenly there is a new tool that can be used to solve problems, and there are people setting problems that require the use of this new tool. And if you never used it before, you will spend a lot of time, you will make a lot of mistakes as with any other tool. So this is why also at this top level you need to spend some time implementing, and the best thing to do is to do this in this upsolving kind of way, because you already spent time thinking about the problem, and possibly you have presentations of solutions like we will have here. So we know the idea of the solution, but you still need to be able to produce working code. And this is the best way of investing the least amount of time to learn to do so. You already have half the work done, and now you only need to do the implementation. So upsolving is very important, and is something I would encourage all of you to do. The grader we are using for these competitions will remain running for a long time, so even after the camp, when you are back home, you have a free afternoon, come back, try to solve some of those problems. All right. To conclude this talk about contest and strategy, there is one more point I want to make. Which is time management during the contest. It is said that contests cannot be won during the first 4 hours. This is about the ICPC contest. During the first 4 hours of the contest, you can only lose the contest by making stupid mistakes and falling behind. But you cannot win the contest. The contest is won or lost during the last hour of the contest. What happens during the last hour of the contest is that many of the teams will solve 0 problems. So, well, many of the teams that still matter. There will be teams at the bottom of the rank list who finally, during the last hour, finish debugging their second or third solution. So, but those don't matter in terms of the rankings. What matters is we want to win, and if we want to win, it's necessary to solve problems during the last hour of the contest. This is difficult. Why is this difficult? During the contest, you have a team of 3 people, you have a single computer. So this means you don't have 5 hours to solve the problems. As there are 3 of you, you have 5 hours of computer time, and you have 10 hours of thinking time. So there is like 15 hours, but you have to use them in parallel. You have to use them during the contest in a smart way. And there are, in each of the contests, there will be easy problems. Those are the problems that get solved at the beginning. And there, you can just use a greedy strategy. Get the easiest problem you see, prepare the solution, and when the computer is available, sit down, type it, get it right, submit it. This is the easy part. The hard part of the contest is when you are getting close to the end. So if you look at it on the time axis, here is 0, here is 5 hours, and now we have 3 people, person A, person B, person C, who can spend their time during the contest. And here, person A will be solving the problem, person B and person C will be solving the problem, and here they solve it on paper, and here they have the solution on the computer, and so on. The problem here is, as you are getting closer to the end of the contest, you have only the hard problems left. And the hard problems may require a lot of time. And what happens to less experienced teams in the ICTC over and over again is something like this. So here is the 4th hour of the contest. And what happens now is that at 4 hours and 5 minutes we have submitted successfully our 7th solution, and now we have 3 hours of time left. But the 3 hours of time are distributed among those 3 people. And there are only hard problems left, and those hard problems do require more time to be solved, so each of them will grab one more problem, and all 3 of them will fail to solve those problems, and nothing will happen during the last hour of the contest. So this is the most common way how we can lose the contest in the last hour. And this is exactly where experience and practice with teamwork can help you. So if you are doing well in the contest, if you are somewhere reasonably close to the top of the rank list, and you suspect that you may run out of easy problems, so if you are getting close to the place when you no longer are sure how to solve any of the remaining problems, then what you should probably do, in most cases is the right strategy, is somewhere around here, you should already have one of the team members start working on one of the hard tasks of their choice. So instead of all 3 people going through the problems and trying to solve them, starting from the easy ones, just take your best problem solver, have them trust the other 2 that they can get the remaining problems you know how to solve, and the best problem solver should start working on one of those hard tasks. And then during the last minutes of the contest, your main focus should be getting this one extra task accepted. So the one person who has been working on it should be the one also with the implementation probably, and the other 2 people who have nothing left to do should be sitting next to them, looking at the code, making sure everything works, because this is also a thing you can practice in practice competitions. Programming in a team, programming in a pair, so not just one person writing the code and the other 2 ignoring them, but one person writing code together with another person who is trying to check everything. If you do it this way, and if you have a bit of practice doing so in a team, so that you know each other and you know how to communicate well, then you can get to a situation where the code you write, you run it, and it actually works. And this is often necessary because often there will be a significant time pressure. You will not have enough time to spend 20 minutes in debugging this last solution. The last solution, you will probably be able to finish it during the last 15 minutes of the contest, and it has to work. So it pays. Usually the best strategy is to slow down to see, like, yes, now we are starting the implementation. We have 32 minutes left. So we can spend 22 minutes on this implementation. We can go a bit slower, and we have to make sure it will be correct on the first attempt. And if you slow down, if you do it carefully, then you can actually do this. And this one extra problem is often what matters. This is the change between having a medal and not having a medal. This is the difference between being the regional champion or not being the regional champion. So this was just like one possible scenario, but the general lesson here is that time management matters, and it matters the most when we are getting close to the end of the contest. This is the risk. The risk is wasting 3 of those 15 hours you have simply because you will be left with problems that are too difficult to solve by a single person within an hour. So during the next contest, try to think about this issue as well. Try to think about time management. Maybe schedule having a strategy meeting at 3.5 hours. Then go through everything, like this is our current state. We know how to solve these two problems. We have no idea about the rest. What shall we do now? And then, at this point, decide about the strategy. This is what we are doing for the rest of the contest. All right. So, that's enough talk about strategy for now. Let's start with going over some of the easy problems of yesterday's contest, and then after a few easy problems, we will have a break. Okay? So, probably the two easiest problems yesterday. The first one was the problem with the pancakes and the two pens. One of the parts of this problem was already shown in the problem statement. If you have two pancakes, you can first put them like this, then you put them like this, and they are done. The second part to discover was that if you have three pancakes, you don't need 4 minutes, you can do it in 3 minutes. And the trick is start with the first two pancakes like this, then put this one to the side, put the other pancakes from the other side. Start cooking the third pancake. So after 2 minutes, one pancake is done on both sides. You have two pancakes which are both done from one side. You finish those and you are done. So it would be first minute, 1A, 2B, second minute, 1B, and 3A, and the third minute, 2A, and 3B. There is one possible schedule for 3 pancakes. Now, if you can do 3 pancakes in 3 minutes and 2 pancakes in 2 minutes, then you can do any larger number, because if you have an even number of pancakes, you can do 2 at a time, and if you have an odd number of pancakes, you do the first 3, and then do the remaining ones in pairs. The only tricky test case, if there's a single pancake, you cannot cook it from both sides at the same time, so you have to spend 2 minutes on a single pancake. Alright, I think there are no questions about this one. The second problem was a problem where we given the string, and you had to produce a permutation such that these are the correct inequalities. Now this is a problem I really like, especially because it has so many different solutions. And there are some solutions that are really painful to implement. For example, a solution looks like this. If it starts with some greater than signs, I will count how many there are, and I will fill in 1, 2, 3, 4 like this. And now there is a less than sign, so I should put a larger value, but I don't know what the largest value is, so there will be some greater than signs. So I will count these, and I want to have 5, 6, 7, so I need to have 8 here. And so on. And this is correct, this can even be done in linear time, but it is so painful to implement. And this is exactly what I was talking about yesterday. It's not enough to find a solution that works. It's always a good idea to think about a better solution in terms of an easier implementation. How can I do this better? How can I have fewer special cases, write less code, make fewer mistakes? And there are very easy ways to solve this problem. One of them looks like this. And the idea was as follows. So we start at the beginning. And for now, we will not care about this being a permutation. We will start, for example, with 0. And whenever we need a larger value, we will use the next unused larger value. So here we will use a 1, here we use a 2. And whenever we need to go down, we will use the first unused smaller value. So from the 2, we will go to a -1, and then to a -2, and again we need to go up, so we will go to a 3 and to a -3. So at any moment, what we need to remember is the interval of values we already used, And the next one should be greater, then we use the next greater one. When the next one should be smaller, we use the next smaller one. At the end, what we will get is not necessarily a permutation, but it is a contiguous range of values, so we can just shift it. So in this case, we will get 4, and this will turn to a 1, and this will turn to a 7, and we will have a permutation. So this was the second best solution, because it's in linear time, it's very simple, but at the end you have to shift it. The best solution goes like this, and you don't have to shift anything. So again, you start at the beginning. And if this value is supposed to be small, then you use the smallest number, and this value is supposed to be small again, so use the smallest number, and this value is supposed to be large, so we will use the largest number, and this value is again supposed to be large, bigger than anything that is one that continues, so we use the largest number still with the news. And again, this value is now supposed to be smaller than this one, so we use a 3, and it will certainly be smaller than anything you will use next. And then you use a 5 and a 4, and you are done. So again, you just need two integers. What is the next smallest value? What is the next largest value? Each time you see a greater than sign, you will write the largest value. Each time you see a less than sign, you will write the smallest value, and you will get the valid combination. So a single for cycle will go from the left to the right, 2 lines of code. If you wrote more than 10 lines of code, this is a lesson why you should think more before implementing. Okay, can you see it? Okay, so the next easiest problem was the problem about the sum of sums of all subsequences. So what we have is a sequence 10, 20, 30, 40, for example, like this. So now we form all of the subsequences of this sequence. We sum each of those, and then we sum all of those sums. So for example, here the subsequences can be like this: 10, 20, 10, 20, 30, 10, 30, 20, 30, 10, 20, 30, and 40, and so on, all the way through 10, 20, 30, 40. And the problem statement said that we are counting only the proper subsequences, so the very last one is the only one we don't count. So if you were to solve the problem exactly according to the problem statement, what you would do is you would sum this, each of the rows, and then you would compute the sum of those sums. The first and maybe only trick of the entire area of combinatorial analysis, so when you're computing finite sums, the main trick is if you cannot sum it in this order, then you should sum it in this order. So change the order of summation. So now the question is, if I want the sum of all of these numbers written here, how can I compute it? Well, it's 10 times the number of occurrences of 10 plus 20 times the number of occurrences of 20, and so on. By symmetry, the number of occurrences is the same for each number. So the question is, what is the number of these subsequences that contain the number 10? And the answer is very simple. If the sequence has like n, and we want to construct one particular subsequence that contains the 10. We have two possibilities here. We either include the 20 or we don't. We have two possibilities there. We have two possibilities there. So together there are 2 to the n minus 1 possibilities. This is the number of different subsequences that contain the first element. but we have to subtract 1 because this one is forbidden. So this is the number of times we should count the value 10, and also the number of times we should count the value 20, and so on. So the final answer is this times the sum of the input sequence. And you don't even need to implement fast exponentiation because n is only up to 100,000, so you can just use a single for cycle to compute this. It's not much of an improvement, but it's good to realize that you can actually afford it in this particular problem. Okay, so let's do one more problem before the break. And this will be the problem twice. So, what we are given in this problem is a large input number. Let's call it n. And we are given a definition that the nice numbers, maybe I think they are called purple numbers in the problem statement, are those where each of the decimal digits appears at most twice. So this number is not nice because there are 3 copies of a 7. And the task is to find the largest value that is less than or equal to n and has this particular property. Now, as soon as you take a look at this problem, you see that, oh, this is a problem with so many special cases and case war. There will be 7 wrong answers before we finally get it accepted. But it doesn't have to be that way. There are ways of solving this problem that are reasonably easy to implement and don't have too many special cases. One of the possibilities how to approach problems like this one is to think about not, well, first of all, if you see a problem like this one, most of the people in the contest will be tempted to solve this using casework. Analyze it on paper, find out all of the different situations that can occur, and then hardwire them to go one at a time. This is not necessarily the worst possible strategy because, well, it works. You will get it finally accepted, but we will probably forget some of those cases, and the code will be very long, and it will be hard to get it right. One other way of looking at problems like this one is that quite often they can be solved easier using some kind of a dynamic programming. In this particular case, there is also such a solution, but it's not that much easier. Still, in general, it is a good strategy to think about it like this. And what would be the idea, the general idea of the dynamic programming? If you are building the number from the left to the right, building the answer, at any moment, you will have some kind of a state. And the state, the representation of the state will be the kind of set of digits you already used. And what is the number of different states? The number of different states, for each of the digits you already used, there can be 0, 1, or 2 occurrences already. You already have in your number. So for each digit you have 3 possibilities. So this will leave you with just 3 to the 10 states. And this can be exploited because 3 to the 10 is a small number. So you could write a code that explicitly goes through all subsets and does something. In this particular case, as I'm saying, it's not that easy, but it's still a good strategy in general to think about problems in this way. Can I use, instead of just writing the case work to find the best solution, can I actually use dynamic programming to go over all possibilities and then to compute the best solution without me necessarily having to go through the cases. But there is also yet another pattern that can be used here, which is kind of halfway between these two solutions. And this is not doing the entire case analysis, but instead trying out a small set of reasonable possibilities, and in each case to use the computer to find the best solution for us. So, what can we do with this problem in order to have a solution with very few special cases? First of all, the largest possible number we can get as the answer is the number 9988 and so on all the way through 00. This has 20 digits, and as soon as the input number has more than 20 digits, then this is the correct answer. So this was easy. What can we do now? If we are left with n that has 20 or fewer digits, we need to produce the number p that would be less than or equal to n. And among all of those numbers, we are looking for the largest one. What does this mean? If we have two different candidates, p1 and p2, we can start comparing both of them to n. And let's say this one equals n on the first 4 digits, and then there's something smaller, so either 1 or 0. And this one equals n up to b here, and there may be 1 next. Which one of them is larger? Well, obviously the second one. And in general, the closer you want to be to the actual value of n, the more digits you have to preserve. The longer is the matching prefix, the closer you are to n, the better answer you have found. So here's the pattern of how to look for a solution. The optimal answer p will certainly have some matching prefix with the number n. So we will start from the longest possible matching prefix, which is if this is L, then we will start with L minus 1 digits, and we will go all the way down to 0. And each time we will do the following. So for all possible lengths of the prefix, we will next look at the next digit. Let's look at the general case. So this is the prefix we wanted to keep. So we have 7, 1, 4, 7, 2. And now we want to make sure that the number is smaller. So the next digit can be anything between 0 and 6. And once again, instead of trying to be clever, we will just try all possibilities. So we are trying all possible lengths of the prefix that is kept the same. Then for the next digit, we are trying all possible smaller values. And now we know that, except for one special case I will mention at the end, the optimal solution is certainly in one of these possible cases. One of the cases we are currently trying. There is some common prefix, and there is some next digit that has to be smaller. And now the only question is, what happens here? And this can be solved greedily. So again, there is no case analysis here, there is just a greedy solution. We already have this. We will go through these digits that are fixed now. We will count the number of occurrences of each of them. We will see some of the digits 3 times. We already know that this is not a valid solution. We just break, go to the next possibility. And if we got here, then each digit had at most 2 occurrences. Then we can find the largest such number greedily. We'll start from value 9. We will fill as many 9s as we have left, then we will fill as many 8s as we have left, and so on. So if we get a given prefix, we can fill in the rest greedily to find the largest such number. And by decreasing this digit, we already make sure that the number is smaller than n. So whatever we fill here will be a valid solution. And this is the entire code. So for all prefix lines, starting with L-1 downwards, and for all possibilities of the next digit, again, we should start with a 6 and go downwards to 0. If this greedy algorithm finds a valid solution, that's the answer. The only possible case when all of this fails is numbers that look like this. Because you cannot decrease the leading one to a 0. And in this case, if everything fails, if even the prefix 0 of 0 blank doesn't give us a solution, then this means that there is no solution with this length. We have to be 1 digit shorter, and in that case, we just immediately fill in the well-known pattern starting from nice, and this is the answer. So for this particular problem, this is the simplest to implement solution I'm aware of. You just like 3 nested loops for each L, for each digit, and then 1 loop to fill in the number from the left to the right. And this is exactly the type of problems I like. There's some algorithmic concept, there is also some reward for thinking about the implementation. Alright, and now is a good time to take a 10-minute break.
Apaga a segunda folha. Apaga a segunda folha. Apaga. Apaga. Não, só pode ter uma folha. Não, segunda folha é para liquidação. Eu perdi o dinheiro para isso. Ô, é sério, pergunta pro Russo. O Russo deixou meu currículo 300 vezes melhor. Coloca outros Waterbot. Ah, é verdade. Eu vou botar no Facebook e perguntou o Water. Coloca o rating. Porque isso não é legal, sabe? Eu coloquei. Nossa, tio. Mas apaga. Cara, eu consigo com esse grande, velho. Eu, o Mark Zuckerberg, não tem uma folha. E ele é o Mark Zuckerberg. Peraí, deixa eu ver.
Eu tô tentando instalar o PDF LaTeX aqui.
Você tá querendo demais.
Só que precisava de um pacote lá de uns libx, sei lá o quê.
Eu li só o pacote de trabalho.
Eles podem instalar as coisas do Source é isso, mas os outros pacotes é mó rolê.
O cara é bom, o cara tem que instalar. É, acho que não precisa. É, pode colocar, né? Graduation, você coloca graduation, e aí você pode colocar um link pra TCC.
Pode me dar também, se eu fiz espaço.
Peraí, deixa eu ver. Sobe. Não tanto. Desce. Extracurricular. Desce. Não precisa ter tido assistente, né? Você pode juntar a MaratonUSP e MDev e falar voluntary on extracurricular groups e tal. Association groups e falar os MDev lá. Por que o Sacobol ficou fora? Você não ajudou? Você pode colocar tipo, tanto o Marvelous quanto o Sacobol, ou você coloca ele junto com o MDev, você já coloca no meio assim do texto, ou juntar os meninos da MaratonUSP e fala Game Development, coloca os dois jogos, não precisa descrever também, eu acho que é mais importante do que a atividade extracurricular, né? Tira isso. Cara, isso aqui é importante. Não. Você tem que encaixar no projeto. Se você colocar esse negócio de você sabe, com uma aplicação, é muito mais valoroso você falar, sei isso. Talvez, se
você no meio
Você está aplicando.
não é uma questão que é
Tipo,
mas talvez se você, tipo, enquanto você. Ó, você o que eu falei pra ele, sabe? Que ele falou, ele colocou os jogos e tipo, MaratonUSP e os Game Dev, tá ligado? Voluntário e tal. Eu falei pra ou junta MaratonUSP e os Game Dev, falar, tipo, grupo de extensão, dar uma disciplina, tipo, falar dos dois. E também junta os jogos um no outro, então Game Developers. E aí talvez no meio disso, tipo, tô falando do MaratonUSP e falo, trabalhando com C++ e tal. Acho que o MaratonUSP dá pra fazer um parágrafo, né? Falar, tipo, programei em C++, fui pra final mundial, fui pra porra toda e tal. E aí no Game Dev, faz um sobre o Game Dev, fala dos jogos e sobre
muito espaço. Você não tem como colocar do lado do nome isso. Então, colocar do lado do nome, você tem que estar levando muito espaço. Eu acho. Mas eu acho legal. A informação tá bem boa. Education. Legal.
Pode usar o cyber do
Pode colocar embaixo, né? Acho que essa parte tá legal. Contribuidor. Fala que você é competidor.
Fala co-creator.
Você não está sabendo que por exemplo, em vez de você falar aqui, sem lua, tira e fala aqui. Written lua. Entendeu? Porque você já tem um certo que você. Onde você aplicou essas linguagens? Qual contexto que você vê? E deixa eu ver, legal, perfeito, 3 pessoas. Vou colocar aqui, por exemplo, quantos alunos tem? Participando do MaratonUSP, entendeu? Fala do talvez não. Place out of 6. Place out of 6. Pode tirar da sua regional. Você quer esportes recentes. Mas é sempre triste você faz as coisas sem tirar depois, mas eu, por exemplo, eu removi o negócio que eu coloquei companhia nova, mas já acho que não tem definido, já tem essas coisas muito novas, né? Mas é uma folha. Mas talvez não aproveitar se eles falam. Deixa eu mostrar até o meu. Mostrar a noção. Não que seja o melhor do universo. Mas isso é muito bom também.
É só assim que faz?
E aí, ó, eu sou basicamente
Ele é muito simples. Não, eu te fiz
que é contrários, que é entendeu? Ó, aí você vai aqui, dá pra saber que eu sei ser mais rápido, sei run. O bootstrap, tá vendo? Quanto eu sei, quanto eu trabalhei com isso. Você vai aplicar
vai ter que ser.
Ela me mandou a tia lá no Facebook. Mandou aquele e-mail pra eu responder as coisas lá. Parece que tem que fazer um MS nesse mestrado, eu acho que é diferente.
Sempre que é
Isso mais preto.
tá muito. Aqui sim.
Eu acho que o meu eu fiz isso.
Passou ainda.
Eu tive uma solução boa pra isso.
Ah, eu tirei o cabeçalho pra falar, não precisa dele, claramente.
Quanto é o tamanho daquele estilo que você está passando por baixo? O overhead da string é assim.
Dá pra fazer uma take com essa porra, né? Deixa eu ver se eu tô mandando lá.
Então eu faço tipo 2 lineares e eu faço.
Não, mas pode pegar o código aqui.
Não, mas é apertado. Deixa eu ver quanto foi esse teste. Compilar. Porque esse foi tipo 6 segundos aí.
Tira, mano.
Vou fazer essa
So this function is the last this part is so I still have what is the expected cost of the next so if you have all expected cost 0
E aí, Damar?
just what Nossa, cara,
Caralho, tem mais uma página, mano. Para o moço. Tá bom, tava sem ficar uma coisa pra vou botar mais pra botei aqui, ó, amarelinho até. Tava vermelho. Já manda a parada vermelha, aí você só tem que
Já manda segundo já e é uma bosta.
da hora. Só fazendo essa corrida em Ladeck, tô errado, cara. Igual toques, velho. Eu tenho template de currículo. Eu faço mesmo um site de currículo, cara. Não sei botar o meu, mas aí esse aqui é muito mais bonitinho. Eu acho que é bom. É que eu quero ver o currículo, cara. Deixa eu ler. Eu quero te julgar. Então, eu tô tentando diminuir ele. Tá com 2 páginas. Você fez isso? Random Walks and Gaps and Random Experiences. Agora pá. Tira game então, eu vou juntar essas coisas que a gente leva e tirar umas coisas da parte.
Com seu nome, por exemplo, esse programa aqui, mas com a meia página.
Vou tirar essas coisas aqui.
Por exemplo, dá vontade de escrever só.
Vou colocar, parece que é melhor colocar no meio dos projetos. Esse aqui,
Esse eu acho que é bem difícil pelas coisas que você faz. Tá falando totalmente na frente. Travesti.
Eu consigo fazer um. Não, tipo, eu não sei como falar. Pagar esse carro só. Ou esse carro super bom, sei lá. Você tá falando da peça que gosta de não, tipo, eu fiz tipo celular, você teve que fazer um grupo e armazenar. E aqui, tipo, uma coisa, X e Y são dependentes. Eu não posso achar o X fazer isso. Depois eu vejo.
Ah, eu já falou que você tinha que ver isso, então. Entendi.
É que é foda, porque é jeito que ela faz uma coisa.
Oh,
Com certeza é mais relevante do que meus
Só mencionar a bolsa é meio relevante, porque a bolsa da faculdade talvez a coisa mais relevante. É, a papatesta conseguir e tal.
Eu vou meio que parecido, porque eu não oficialmente tenho a bolsa de assinar um bagulho aí lá, mas tudo bem, né? Pelo amor.
Bolsa, papatesta, período, futuro, mais pra frente. Ouvi dizer que eu vou ganhar.
Vencedora mundial, maratona de preparação, 2019. Se a gente tivesse conseguido passar por mais.
Okay, get ready and we can continue with the others. Okay, so to start the second half of this session, we'll start with a very easy problem. Well, problem is not very easy, but has a very easy solution if you think about it the right way. And this is the problem of answers. So in this problem, what we have is a contest with different competition tasks. And task I has CI people who solved it. And we know that there is a threshold S with the meaning whoever solved S or more problems advanced to the next round. And the question was, given just this information, compute the largest possible number of advancers. At the first glance, this seems to be an easy problem because there's just a few numbers, how hard can it be? But it turns out to be the case that directly solving the problem, directly answering the question, is very hard. It is possible. There are some complicated greedy solutions that work. Essentially, what you can do is do something like gradually try to increase the number of advancers and redistribute those solutions among those people and so on. It can be done, but it's very painful and it's hard to discover such a solution. Instead, we will use the technique I already mentioned once during this camp. The technique is as follows. If you have any number of advancers, then obviously all of the smaller numbers of advancers are also possible, because you will just ignore some of the people and say that this was a bad person, these were different people who solved those tasks. So this means that the question we are trying to answer has this monotonous property. There are until some value, we can assign this problem, the solutions to people in such a way that we will have many advances. And from some value on, this is not possible anymore. So what we can do is we can turn the optimization problem into a decision problem. Instead of asking the question, what is the maximum number of advances, we can ask the question, is it possible that there are exactly k advances? And if you haven't encountered problems like this one before, it can come as a surprise. What can the difference between the difficulties of these two questions be? So the original question was hard, but this one, verifying a particular value k, turns out to be very, very easy. But because, let's take a look at what we have to do. We can imagine it like this. We have k separate bins. Oh, let's draw them upside down. This will be nice. So we have k separate bins, and we have these n competition problems. Each competition problem, when you solve it, gives you balloons. And for each problem, the balloons have a different color. And now what we have to do is we have to take these amounts of balloons and distribute them among the k contestants in such a way that each person will get S balloons of different colors. And now comes the main reason why this is easy and the original question was hard. Because we will not have to deal with different boundary cases. In particular, if there are problems, Ci is greater than k, or even greater than equal to k, what we can do is we can take such a problem and give every person a balloon for the problem. There may be some balloons left, but we have no use for those. And these extra balloons are precisely what complicates the situation in the original problem. Because if you don't have a fixed number of advances, if you don't have a fixed value of k, then maybe you can use these, maybe you don't, and depending on different values of k, this can change. So in the original question, this is called complications. In this question, this is painfully obvious. If you have a problem with a lot of balloons, just give everybody a balloon. So you do this with all such problems. So you already have some balloons for all the contestants. And now you have the remaining problems, the problems where you have fewer than k balloons. What can you do with those balloons? You will just go in a round-robin fashion and hand out the balloons from the first such problem, the second such problem, the third such problem, and so on. If you do it like this, there is no risk of giving two balloons of the same color to a person, because for each color, we only have fewer than k. So if we start handing them out, we will run out of those balloons before we get back to the same position. So this will certainly be valid, and we will use all of those balloons, or we will fill in all of the buckets, whatever happens first. So in order to verify k, you just do this. You go through all of the tasks once, find the ones that give us a lot of balloons, and each of those essentially decreases S by 1. And then you take all the tasks that gave us only a few balloons, and you distribute those balloons, and you don't have to actually distribute them. You can just sum all of those values, and at the end check whether it is more or equal to this times k. So this is just a very simple for loop to verify whether or not there can be k advancers, and using this as a helper function, you can then binary search for the maximum valid k. One final word of advice is that the limits for this particular task are kind of large, and there can be one nasty overflow if you are doing the binary search, if you are using signed 64-bit integers, and you do somewhere in your binary search low plus high, then this will overflow. So you need to be a bit more cautious and pay attention to the bounds for all variables. Yep.
You could do this problem with just non-long without a high non-long.
Yes.
If you do like high minus low.
Yes, exactly. There is this way of writing it of low plus high minus low divided by 2, and this doesn't overflow. Okay, so for the next task, the next task will be the one with the party. So we are in the rectangular plane. We have Manhattan distances. We have a collection of rectangles. Each rectangle contains some houses. And the question was, which of the houses minimizes the total Manhattan distance from all other houses to this one? And we know that the total number of these points is up to 1 million. So what can we do here? Well, the most important thing to realize about Manhattan distances is they are kind of independently divisible into those two different dimensions. So if you are going from here to there, you can read as two separate parts of the journey. One of them is horizontal and the other is vertical. So if you are asking the question, what is the total distance if we want to assemble everybody on this location, it can be asked as follows. What is the total distance people have to travel horizontally in order to get to this coordinate, plus what is the total distance people have to travel vertically to travel to this coordinate? Because each person will travel some distance horizontally and some distance vertically. We can sum these up independently. So these are the questions we need to answer. And essentially, what happens here is that we have two independent one-dimensional problems. So let's just look at one of those directions. So what do we have is we have 3 points here, we have 3 points there, we have 5 points in this location, 5 here, and 2 here, and 2 here. And now for each of these locations, we are asking the same question. What is the total distance the people will travel if all of them want to meet here? And this can be computed quite easily in linear time. To begin, you will compute it for the leftmost location. This is just a simple sum. Here we have 3, and each of them will travel 1. Here we have 5, and each of them will travel 2. So this is 5 times 2, plus 5 times 3, plus 2 times 5, plus 2 times 6, and we have the answer for this coordinate. And now whenever we move one step to the right, what happens? When we are moving from here to there, we are moving the meeting point closer to all of these, and we are moving it away from all of these. So here we are moving it away from 3 points and closer to n minus 3 points. So the total change of the distance traveled is the distance here minus n minus 3 times this distance plus 3 times this distance. And in this way, we can recompute the sum distances in constant time whenever we move one step to the right. We just need to keep track of how many points are already on the wrong side of history and be moved away from. So the easiest way to do this is just to assemble all of these coordinates into a vector, then call a function, and then store the answer for each of the coordinates in a map. And you do this once for one direction, you do this the other time for the other direction, and then you iterate over all points, and each time you ask the question, what would be the total cost of travel if we want to meet here? And the answer is always the sum of the answer for this coordinate plus the answer for this coordinate. So you iterate over the 1 million possibilities and you will get the answer. Okay, and now for a more interesting version of this problem, as I promised yesterday, the problem is also solvable with much higher constraints. In particular, we could solve it for any collection of non-overlapping rectangles, such that the number of rectangles is up to 10 to the 6, and the areas can be large. How do we do it? I'll give you just a general idea of the coordinates. Let's go back to the one-dimensional problem. So for this one-dimensional problem, let's ask the following question. Given these locations of people on the line, what is the optimal meeting place? And it turns out to be the case that the optimal meeting place in the one-dimensional problem is always the median of the coordinates. Why is this the case? Well, imagine that we plant a flag here. There is like this. There is a flag, and the flag denotes the optimal meeting place. And now we can take a look at the people who live to the right of the flag and the people who live to the left of the flag. And if there are people in the flag directly, then those will be apparently what happens to them. So now the question is whether it is better to move the flag in one of these directions. And if it happens to be the case, then more than half of all people live to the same side of the flag, then all of them will prefer the flag to go towards them. And if you move the flag towards them, you are decreasing the distance to the flag for more people, and you are increasing it for fewer people. So you are optimizing the sum of distances. So the optimal spot has to be such that on either side, the number of people is less than half, or at most half. And this is why the optimal answer in each direction is the median. How does this help us in the original two-dimensional problem? Well, we cannot just directly choose the median of the x-coordinates and the median of the y-coordinates because those are independent, and it can be the case that it will turn out to be some point outside of the rectangles. But what we can do is for each rectangle independently, we can ask the question, what is the optimal choice within this rectangle? And then we can do this process. So in each direction, if this is the optimal location of the median, then we want to be at this exact coordinate. So this is what happens in this direction. And in this direction, if the actual location of the median is to a side of the rectangle, then we want to be as close as possible to the side. So within this rectangle, this would be the optimal choice of a meeting place. In this way, for each rectangle, we just get a single candidate, and then for each of these candidates, we evaluate the sum of distances and we choose the best one. So this would be a solution for a more general version of this problem. Okay, does it make sense? Are there any questions? Yeah?
Why the closer point to the median is not the optimal answer?
I think it can be. I didn't claim it wasn't. I just didn't want to. I didn't spend any time thinking about this question because I already got far enough to solve the problem. But yeah, I'm not sure. You can think about it and you'll see. It may be the case that it is the optimal answer. It might be the case that it isn't because I'm not sure at the moment. No. I don't see it, and in an actual contest setting, given this particular situation, whether I can either think about it or implement this before it works, I will go for the second one. But yes, I'm intrigued by the question, and I will also spend some time thinking about it and discussing whether or not it is true. Okay. problem is a problem about numbers with repeating units. So we have a number that consists of n ones. We multiply it by itself, and then we get such a nice pattern as the result. And the question was given a very long number this time, and a short segment of the result output the digits of the segment. There are two ways of solving this task. One of them is to actually write the code that works for smaller values of n, observe the pattern, guess the pattern, hardwire the pattern, submit, and hope it's correct. The other possibility is actually doing the multiplication. So if you imagine the long form of the multiplication looks like this, what happens here is that in this column we have a single one, in this column we have two of them. And if you give me the column number, I can compute the number of ones in this column in constant time, because well, in column n, there are exactly n ones, and as you are going to the either side, the number of ones increases by one in each step. And now, if we are interested in some range of the result, we could just directly take all these values, so this would be like 4, 5, 4, 3. If there would be a larger product, very many ones times very many ones, and we want some range of the result, then it can be the case that the number of ones here would be 18, 19, 18, 17, and 16. These are not actual decimal digits, but we can do the carries, so this would be just the A. Instead of 19, it would be 19 plus 1, which is 20, which would be a 0. 18 plus 2 is again 20, which would be 2, and this would be a 9, and this would be a 7, and this one, this carry would get lost. And this would be almost correct, except for the fact that there will be also some other carries coming in from the left side, and these may change the last few digits of this number. And now the only thing that is left is to guesstimate how many additional columns I need. We already know by observing the small cases that the pattern here is always such that the digits are roughly repeating 0 through 9 in some pattern. So the important observation here is that there will never be very many 9s in a row. So there will never be a situation where I carry somewhere here and flip all of the digits all the way through this number. So you take some reasonable margin that's wide enough that I did in my solution at 50, and I was certain this is large enough. Then you should be safe. So you do this computation, you take all of the columns you're interested in, and maybe up to 50 to the right, or stop at the end of the number if there are more columns. In each of them, you sum the number of ones, you do the carries, and you simply output the part of the arrays. If you are unsure about this constant 50, what you can also do is you can keep on adding those columns one at a time, doing the carries, and then when you see the actual digits you have in the result, then you can also write a terminating condition saying that whatever appears here, it will not be enough to carry over to the range that interests me. But it should be reasonably easy to do, given a correct mathematical proof that the carry cannot go farther without the something like the logarithm of n should be roughly the length of the segment of the range mean. Okay, let's go to the next problem that got some reasonable number of solutions, and this is the problem about collisions. Yeah.
You said that I only have to know the 50 numbers before the beat.
Yeah.
But the numbers before this 50, they are not important to know the carries of the 50.
No, because it's like this. So you have the input number times itself. This is the range of the result you actually want to know. And suppose you already computed a few digits afterwards. and you see that these are 2, 7, 3, or so 4, 3, 2, or something like this. And now if you take one more column, you know the value of n, and this sum in this column can be at most n, and even if you add the carries from the previous columns, the most you can get as a carry here is n divided by 10. And if n divided by 10 plus 432 is less than 100, less than 1,000, then the carry cannot go through the reason. So if you have a large enough segment of values that are significantly smaller than 9s, then the carry cannot be large enough to measure all the way through there. Is it okay?
You are saying that.
Yeah, like I'm doing a very specific example. So for example, assume that n is 470. This is the actual range you want to compute, and you already did all of these columns. You already did all of these columns extra. So you know some values here, and you know that these are 4, 3, and 2. Now in this column, as n is 470, then this means this is 470. So when you add this column together, you will get a value here that is at most 470, and also here at most 470, and the same is true for all the columns to the right. So if you do the carry from this one, you will get at most plus 47 here, so this will leave you with something like 51 plus 51 here, and this will leave us with something like plus 52 in this particular column. And now 432 and plus 52 is still only 487 or something. And so this carry, even though if there are all of columns here, the carry still won't influence anything beyond this line. The carry will stop in this part. In general, if these would be any arbitrary numbers, you could have situations where you would have many 9s here, and then it could be the case that all of the columns in the right manner. But in our particular case, we know that the result has a nice shape, there are patterns of repeating digits, and you will always get the long enough sequence of 3, 2, 1, 0, and so on. And this will stop the carries from the rightmost columns. So when we are doing string hashing, it is a common practice to take to consider the string to be a large number. So string is sum is 0 to s n minus 1, and the value of the string can be expressed as a sum. I go from 0 to n minus 1. As I times a base to the power of I. And now when you want to hash this particular string, you just take the value of this hash function, modulo the size of your hash table, or modulo some usually random prime that should give you a reasonably small fingerprint of the string. One of the important things when you are doing actual hashing in practice like this is the choice of the base. And in particular, the choice of the base should be such that the base is larger than any of the digits you can use, any of the SI. So if I'm using standard ASCII in the strings, then I would use a base of 256 or 257 or something like this. And this problem is showing you why it is the case, because if you use a base that is too small, in this problem we are using 31, you'll get a situation where different strings will have the same exact value as the large number. And now it doesn't matter what is the prime you choose, what is the size of your hash table, such things would always cause a collision. And this is a bad thing, you don't want to happen. So in this particular problem, what we have given was one single specific string S, and we wanted to count the number of such collisions, number of different strings that have the same hash value, the same value Z as this particular string. And one important thing we know from the problem statement is this inequality. We are using the printable range of 17 ASCII characters, 32 through 126. So, what do we do with this task? The first observation is that in order to have a collision, we need to have strings of exactly the same length. Why is this the case? Well, because if you have two strings that have different lengths, one of them is shorter, the string S and the string T. Even if there is one extra character, and the extra character has the smallest possible value, which is 32, it will still be multiplied by a higher power of 31, and the total value would be larger than anything you can get from S. So even if S is a sequence of 126s, and T is a sequence of 32s, which is one longer, if you do the math, you will see that Z of T is larger than Z of S, and therefore they cannot be equal. So now we are looking at strings of exactly the same length. And the key observation here, we want to count the number of different combinations that will have the same hash value as S. Is the same you could have seen, for example, in problems about weights. If you have balanced scales and you want to weigh something, and you have weights that are, for example, the powers of 3, then you can do this observation that yes, all of the weights are divisible by 3, except for the smallest one. So now, from the remainder of the weight modulo 3, I can see where to place it. And this process is the same thing that's happening here. If you look at the value Z of a string, it is a sum of many terms, and all of the terms are divisible by 31, except for a single term for the first term, which is S0 times 1. And the same will be true in the expression for the other string T. So, if you look at those first two characters, what we get is it must be the case that S0 and T0 give the same remain to their modulo 31. If this is not the case, we can immediately conclude that the two strings cannot have the same Z value, because the values of those two strings will be different modulo 31. So in order to have the exact same Z value, the strings have to have first characters that satisfy this inequality. Now it can be the case that those two characters can be exactly equal, but it doesn't have to be. So we may, for example, if S0 is 32, then T0 can also be 32 plus 31. What happens in such a case? In such a case, we can then move on. We can ask the following question. We can just look at the rest of the string S and the rest of the string T, but now we are not looking for two strings that will have exactly the same hash value. Now we are looking for two strings, S prime and T prime, with the following property, that Z of S prime plus 1 equals Z of T prime. So what happened here is that this particular character made it so that Z of S plus 31 equals Z of T. And if we take away these first characters, so we divide everything by 31, we will get us here. So if we are looking for strings S and T such that they have the exact same value, sorry, like this. So this is what we want to keep. This is what we know about the first characters. And now when we take this equation and we divide it by 31, this is what we will be left with. So on this character we added extra 31. So in order to compensate, we need to add 1 here. So now we are looking for the rest of this string and the rest of this string, and they should have this property. And now we can do the same thought process again. We can look at this character and this character, and this time it must be the case that this character plus 1 must be equal to this character modulo 31. And again, we will get a few small possibilities what that character looks like, and we can go on and on. Sorry. So what happens here is at any moment we are always solving questions of this type. We are left with the suffix of the original string S, and we are left with this delta between those two strings. And the delta will always be very small. This will always be a value between, I think, +4 and -4. So now what we can do in order to finish the solution is we can simply apply normalization. So if the length of the string is n, the number of sub-problems we are solving is n times 9, so it's only linear, and for each of them we'll compute the solution, what is the number of such strings, such pairs, and we return it. So again, to summarize, the entire solution is a recursive solution that starts by calling what is the number of strings such that they match the last n characters of the string S, and the delta is 0, so we have an exact match. Zs must be equal to Zt. And recursively, when we solve this problem, we go over these other sub-problems, one character at a time. Alright. Was this clean enough? Are there any questions? Yeah?
What happens when you go over 126? Like when you carry?
This will never happen because, well, what happens here with, for example, the +1, and you already know this character, so you know that S1 is 62, then the possibilities for T1 would be 63, 32, 94, and 125. These are the 4 possibilities you have. And these ones will lead to the next query, which will be solved for the last n-2 characters. And the delta will be either -1, 0, 1, or 2. So the delta cannot grow arbitrarily. The delta is always only within the difference between this particular ST, SI, and TI within this range, and it can be only very small. Next, problem whiteboard. And this is the problem where many of you got scared by seeing that nobody solved it and then you didn't attempt to solve it. This is actually a reasonably easy problem. What do we have here is in the whiteboard. On the whiteboard, there is a pattern of red and white squares. And we are given a description of a path that somehow went through all those squares. And we know that we have a marker that originally started to paint everything red as we went along the path, and suddenly it dried out, and from that point on, it erased everything we went through. And the question is, given the final state of the board and the path of the marker, verify whether this was possible and compute something about the time when the marker could have dried out. So, what do you do in this problem? If you have the problem statements in front of you, there's a nice example at the end with also a picture of the board. For now, let's imagine that we do this solution exactly step by step by simulating what is happening. So we will start in the bottom left corner. And we can do something like this. We will walk along the path of the marker, one step at a time, and we will print the timestamps into the cells we are visiting. It may be the case that we visit the same cell multiple times, and in this case what we will do is we will just store the timestamp of the last visit. So this will be only 13, this will be only 14, and this will be only 16. Why is this the case? Because only the last time we enter a cell matters. Even if we went through a cell 10 times, the first 9 times don't have any influence on the final color. The final color is red if the marker was still drawing when we went there last time, and the final color is white if the marker was already erased. So only the last visit matters. So we know the situation looks like this. Now, if there is a red cell that hasn't been visited at all, we know that the answer is impossible. This cannot happen. Otherwise, if all of the red cells are not the visited ones, now we have information. If a cell is red, it means that at this particular time, the marker still had to work. So if the cell with the timestamp 8 is red, at time 8, the marker must be working. If cell 15 is white, the marker must already be dry at time 15. So each red cell gives us a lower bound, and each white cell gives us an upper bound. If those two are not in conflict, so all of the lower bounds are like this, all of the upper bounds are like this, then this is the interval when the marker dried out. This is the answer we print. And if those are in conflict, then again there is a contradiction and there is no answer. So this would be the entire solution, were it not for a small, tricky part of this problem. And the small, tricky part of this problem is that the constraints are a little bit deceiving. In the constraints, everything seems to be up to 10 to the 6. All the area of the whiteboard is up to 10 to the 6, and the number of movements is up to 10 to the 6. But there are some problematic cases that can occur. There can be a case where the board is 1 times a million, and there are a million instructions how to move the marker, and each of them needs to go somewhere from the left to somewhere to the right, and in this way, their marker will make up to 10 to the 12 unit steps. So sadly, we cannot just do the direct simulation one step at a time. We need to be a bit more clever. What can be done? Probably the easiest way to implement this is just to take all the movements of the marker and store each of them within the corresponding row or within the corresponding column. So if you have a movement of marker like this, then you will have a record for this row, and into the record for this row you will enter something like, we start in column 3 at timestamp 15, and we move towards column 6. So for each row, you will get a separate collection of movements of the marker within the row. For each column, you will get a separate collection of movement of the markers in this column. And now all you need to do is process each row separately, process each column separately, and if you have a collection of movements of the marker within the row, you can use the fact that they are all disjointly timed. So either all of this happens before all of this, or vice versa, and you can just do sweeping within the row. So you go from the left to the right through the intervals. You maintain which is the topmost interval, the one that happened last, and as you are going through the cells, you are filling in the values from the particular last pass to those cells. So if this one was doing 15, 14, 13, and this one was doing 7, 21, 22, 23, 24, then this cell will get still 15, and then next cells will get 21, 22, 23, and 24. And you do this for rows, you do this for columns, you take the maximums, and you will get exactly these values you need. So this is a little bit annoying in terms of implementation because you can have passes that go this way and passes that go that way, and you need to handle it. But conceptually, this is a reasonably easy task. Okay, any questions about this one? So what's left?
Distance, the implementation on the rows, it should be linear, or n log n is enough?
Yeah, well, there is the extra logarithm. The extra logarithm is the logarithm of the number of things in this particular row.
Yeah.
So it means it is the most log of the number of movements in each row. And so you take all of the movements of the marker and you divide them between rows. So each of the movements of the marker is only processed exactly once. So there is only like an extra logarithmic factor to be for this. So it is 1 million times log of a million or fewer. No, so now we are left with 3 problems with almost 0 success rate. The first of these problems is mostly an implementation problem. This is the problem of the resistance. To begin the solution, the resistance is actually an existing board game. It's kind of fun. If you don't know it, give it a try. And for the actual solution, what we need to do is essentially just the brute force search of the state space. So you can iterate over all possible subsets of people who would be the saboteurs, the spies, and for each of them you can evaluate whether it is plausible. So you discard those that don't match the observations you made. And now, as you know that at the beginning the spies were chosen uniformly at random, you know that each of those cases that we made that are plausible, given the history, must have the same conditional probability, and then you can just average through all of those and compute the answer. There is exactly one place close to the end where you need to do some kind of a small smart computation of the answer. So when we are trying to what you can do is, if this is a possible set of spies, then I can iterate over all subsets of people who can go on a mission and aren't spies, and for each of them increase the probability that will be the value I output. And if you do it like this, it should be fast enough. So the outer loop of the solution iterate over all possibilities for the spies, and within the loop you verify whether this set of spies is consistent with what we know, and if it is, then take the probability of this happening and increment the answer for all of the possible subsets of people who are not spies. So in this way, we can just compute the result and output the best solution. So it's not algorithmically hard, just annoying because there is a lot of details you have to pay attention to. And also, it is really helpful in problems like this one if you are already fluent with working with big masks, because those are a very easy and good way to represent the subsets of people and such. There are easy ways to iterate over subsets of fixed size. If you cannot do it with big masks, one of nice ways in C++ how we can iterate over all k element subsets of a set is you just take an array that is some zeros and some ones, and the length of this is n, and the length of this is k. And now what you can do, you can repeatedly call next permutation of this array, and in this way you will iterate over all possible sequences of zeros and ones, each of them exactly once, and the ones are always telling you k element subset you should try. So if you want to iterate over all combinations of k spies among n people, you can do it also using next permutation like this. Okay. Next problem was the problem called character comparison. In this problem, we are given two bitmaps. We were told that the bitmaps represent some characters, and our task was to check whether they are topologically the same. So what do we have is a collection of connected components. In this case, there's one here, the second one here, a third one there, this is the fourth one, and this is the fifth one. And some of those components are nested inside each other, so this component is contained within this one. And the first part of this problem is to actually parse this representation of a character. So we need to do some kind of a breadth first search or depth first search on the picture to find the actual connected components, and also to be able to find the way they are nested inside. So we will start from the background color for those that are touching the boundary, and then in each iteration we will then whenever we find an uncolored cell, its colored neighbor is the number of the outer layer that contains you, and then you can fill this one, and later on when you get to the other ones, you will already know that they are contained with you, and so on. So, in this way, if we parse each of these pictures, what we should get is a tree of these connected components. So, here are the outer ones, and usually the leaves of the tree, and all of the rest, the other way around. The outermost component, the boundary, is the root of the tree, and each time you have a component, the component can contain other components of the opposite color. So the node for this component will have children for each of these, and then if this one contains another white ones, these will be children of this one, and so on. So in this way, each picture corresponds to a tree. And the question whether those pictures are topologically equivalent is actually the question whether those trees are isomorphic. So what we needed to implement then, after parsing the ugly representation, was a check of tree isomorphism. And the way to do this is in each of the trees, we will go from the leaves to the root, and you will assign a numerical value to each node of the tree. So let me illustrate with just pictures of trees. Sorry, this. This, like that. So at the very bottom, what we will do is a leaf that is white will get a 0, a leaf that is black will get 1. And as you are going higher in the tree, what you do is when you have a vertex, and the vertex has some subtrees. For each of the subtrees, you look at the value, so this can be, in this case, for example, this vertex has one subtree and the value is 0. This vertex has one subtree and the value is 1. You take this sequence of values, so it could be 0, 0, or 0, 7, and 0. You sort the sequence 0, 0, 7. And if you have seen this exact sequence before, then you know the number you used to represent the sequence. And if you haven't seen it, then you increment the number of different trees you have seen, and this will be the new identifier of this entire subtree. So in this case, a tree with a single child, which has a 0, is something we haven't seen yet, so this one will be a 2. A tree with a single child, a node with a single child which has a number 1, is something we haven't seen either, so this gets a 3, this gets a 0 as well, and now this is a 1. Here we have a node that has 2 children, a 1 and 2. Still, again, this is something new, so this will get a 4. And if there would be another such tree somewhere here, so a tree with a white node, 2 black nodes, and the white node, this one would be a 0, this one would be a 2, this one would be a 1. And here, again, we see a 1 and a 2, which is the same as 1 and a 2. So this one will again get a 4. So the way we implement this is you have a map where the key is a vector of ints and the value is a simple integer. And each time you process a new node, you take the values of its children, you sort them. If it's already in the map, you know the label for the node. If it's not, you will increase the counter and give it a new label. So here we have 0, 3, 4, 4, you get a new label 5. And you do this with both of the trees at the same time, and then you just compute the value, compare the values for the two roots. This is not the optimal way to compute tree isomorphism, but it's fast enough for this particular problem, and it's very easy to implement. So the ugliest part of the solution is going from the beta representation to the tree, and then this part is actually quite easy to implement.
Can you talk a little bit more about how to parse the graph into the grid into the tree?
Yes. Okay, so the solution will look like this. Okay, so first of all, we have the boundary color. So we can imagine that the bitmap is actually one cell larger, and everything here is the boundary color. So this will be the background component. Now the thing you can do is you can do the standard algorithm to just find the connected components. So you will iterate over all of the cells, and whenever you find a cell that hasn't been marked yet as a part of a process component, you will start a new search from this particular cell. So in this way, we will number the connected components. This will be component 0. We will color everything component 0. Then we will go continue with the search, find this. Everything will be component 1, and so on. And now the thing to realize is that you already almost have also the information about nesting. The only thing to note is that your parent component is the component that is adjacent to you and has a smaller number. And in fact, you can compute this information on the fly, because if this is the first cell of the new component you are processing, then the previous cell, which is either this one or this one, if this one is not present, well, there has to be always this one cell, so you just look there, and this is the number of your parent. So in this way, in time linear in the size of the picture, you can not even construct a connected component, but also construct an array of parents. So the parent of 0 is undefined, parent of 1 is 0, parent of 2 is 1, parent of 3 is 1, and 4 is 1, and so on. And this is the entire representation of a tree. You can then turn it upside down. So instead of for each vertex having its parent, you will for each parent have a list of its children. And then from this representation, you can already do the isomorphism algorithm.
Thanks.
Yep.
This problem has some concepts from the topology branch of mathematics, and it seems it's useful to resort to graph theory to approach the problem.
Yes. Usually, if you see problems based on topology in programming context, this will be the case that the topology is there mostly to scare you, and you need to find an equivalent formulation of the task that doesn't use topology anymore. So in this case, you need to realize that that structure of adjacency has to be a tree. This is an important observation in this problem. It is not an arbitrary graph. You cannot have arbitrary adjacency between the components, but they are contained with each other. This implies that it has to be a tree when you draw all of the edges between the adjacent components. And as soon as you are comparing two trees, whether they are isomorphic or not, this is an easier problem. This is a problem that you don't have to regard topology, and you can just manipulate those trees as discrete structures. There has been a task in the Polish competition, that actually used topology. This was a task about some fish swimming around. So you had a bitmap of water and obstacles, and fish swimming around those obstacles, and there were just questions whether two trajectories are equivalent or not. This was actually painful to solve. But it's the only case I've seen where there was a task really about topological equivalence that could be reduced to something simpler. Okay, and we're left with just a single remaining task, and this is the task about the chocolate game. I admit I will not give you a full solution of this problem, because solving this problem completely requires quite a lot of theory. If you have no experience at all with combinatorial game theory, I suggest as a starting place, it's easier to start playing around with symmetric combinatorial games. So these are the games where in a given situation, each player will be able to do exactly the same moves. A canonical example of such a game is the game of NIM, where you have some tokens and some piles, and each player, when it's their turn, have to remove some of those tokens, and whoever doesn't have any move, doesn't have any value move, loses the game. So, as long as the game is symmetric, there is a lot of nice theory behind these games, how to solve them. In particular, there is a theory called the Sprague-Grandi values, which says that in the symmetric games, each position of a game is kind of equivalent to a single pile of the mean game, and you can use this to combine games easily. So there is the notion of like the sum of games. You have several independent things, several independent parts of the game, and the actual move consists of choosing a single part of the game and making a valuable there. Then you can, then we have tools that tell us how to analyze each of the parts separately and then combine those results. So instead of dealing with one very large state, which is the product of possibilities in all those small games, we can just analyze each of the small games separately and compare those results. And there's, as I was saying, a lot of very nice theory behind this. And then you move these asymmetric games, the games that are called partisan, where each of the sides has a different set of moves, which is also the case in this chocolate game. The chocolate game, one player was only allowed to break rows, the other player was only allowed to break columns. So you have a piece of chocolate that is 1 times 7, and one of the players is completely done and has no value moves left, and the other player can still make 6 moves on this board. And it turns out to be the case that when analyzing these asymmetric games, we can deal with the concept of like a move advantage. And each of those separate pieces of the game will be advantages for one of those players. Maybe it will be like exactly fair. Exactly fair would mean that whoever starts will lose. And compared to this state, there can be some pieces that give extra like free moves to one of the players or to the other. And we can evaluate the position by summing up these extra moves and saying whether the total is in favor of one of the players, in which case the answer is that the player always wins, regardless of who starts, or whether the total is exactly 0, in which case the answer is that the second player will always win. So for this particular game, it has 2 nice properties. One nice property is that the answer is never first. That's why it's not in the examples as well. And the other nice property is that the move advantage for each position in this particular game is an integer. It doesn't have to be the case. And there is again a lot of very nice theory behind these parameter games. There are nice books, for instance, the original book that deals with this are Conway's books on numbers and games, and then books in Brains for a Mathematical Place. In these, there are different examples of such games, and you can have concepts like the advantage is half a move, which means that if you take a position that is half a move advantageous for one player, you copy it, and then you add another position that is known to have one move advantage for the other player. You will get the total situation in which the answer is that the second player will win. And there are also other nice concepts. So, if you haven't seen the theory behind this, I recommend the area wholeheartedly. It is a very nice area of nice combinatorial problems. Different concepts will appear at different parts of exploring this area, for instance. You start playing with these combinatorial games, and at some point in time, Conway will introduce a new way to define the real numbers, and suddenly we will discover the real numbers are still not enough to describe some of the games. So there's a lot of things to learn before you can tackle problems like this one, if you haven't yet. But one nice thing you can do and should do in order to learn at least a little bit about how this game behaves is you can solve an easier version of this problem. The easier version would be that at the beginning you only have a single piece of chocolate, and for this single piece you need to answer who will be the winner. You both press very optimally. What you can do is you can implement a brute force search of the search space, of the space. So we'll try like all possible ways how the game plays out. Whenever you see 2 symmetric pieces in your space, you can move those to prove the search. And once you do so, you should be able to solve all the small instances for just one single small rectangular piece of chocolate. And if you do so, you should see a pattern of what's going on for the single instance. And the pattern will tell you that somewhere in the middle, if the piece is roughly, but not exactly, a square, the game will be a tie, so whoever starts will be then forced to lose. And somewhere to the sides, if the rectangle is very narrow, then one of the players will already have an advantage. And from this, you then could be able to guess what exactly, how much is the advantage for this player, and the full solution then sums up these advantages somehow. So I think this is how far you can get without a theory. You can try experimenting with this gameplay just with a single piece of chocolate, and you can realize that not just for squares the game is bad. Alright, so I think that's all for today, and lunchtime and then a contest.
Pô, cara.